I'm going to sketch a depiction of what happens here, and for reasons it'll become apparent, I'm going to have my x naught, y naught here, and I'm going to just consider a delta y interval in this direction and a delta x interval in this direction. Now, in our three-dimensional coordinate system, a delta y in this direction would be positive. With the usual orientation, our delta x in this direction would be a negative change in x. And that's okay. You'll see why we do this in a minute. It just makes the picture much easier to draw, and then we can generalize to the question of error analysis. Okay, I'm going to complete this rectangle. So now here I've got the point x naught plus delta x, y naught plus delta y. At the point x naught, y naught, our calculation of z, which corresponds to something in the real world, recall letting that correspond to an acceleration, we'll have the value f of x naught, y naught. If we move a distance delta y parallel to this segment, we're going to end up at a point here. And our value of y is going to presumably increase. When we calculate our derivatives, we'll find that our value, and I said our value of y will increase, our value of z will tend to increase. Recall that z tends to increase with increasing y, so this will presumably cause the value of our function to increase. Our function is, the value of our function is z. So we have a triangle here where this altitude of the triangle is the change in the value of z due to this change in y. Now we also have a change in x, so we can sketch a line parallel to this one. And if we come up to here, a distance equal to this, then move back parallel to our x-axis, we have a rectangle moving back in the x direction. Then our change in x, our change in z due to this change in x, since x is in the negative direction, delta x is in the negative direction, recall that we observed that the function that we're using will tend to decrease with increasing x. Similarly, it increases with decreasing x. Now x is decreasing, so that our function, let's say, changed by this much due to the change in the x. And now we have a triangle back in this direction. This change is equal to the value of the y derivative evaluated at x naught, y naught of our function f times delta y, and back here we have a delta z equal to the x derivative evaluated at x naught, y naught times delta x. We can complete a three-dimensional diagram, and it's going to get a little messy with the labeling and so forth. But we can come up here, we can come up here, and similar to figures that we've drawn before, we can draw a triangle similar to this green triangle up here. And we can say that as we move from x naught, y naught over to x naught plus delta y over to this point, and then to our final point, x naught plus delta x, y naught plus delta y, we have this change in z added to this change in z. Now that's the case to the extent that this triangle is similar to this triangle. Remember, this function is changing, and the slope of the function in the x direction might well be changing. But to the extent that the triangles remain similar, we're going to have a triangle here, and I'm going to make that green, and this should be similar to this triangle. So we'll indicate, is this triangle similar to this triangle? Now, if delta x and delta y are small, then this function won't have a lot of room to change its behavior, so that the y derivative at this point should be pretty close to the y derivative at this point, and the x derivative at this point similarly pretty close to the x derivative at this point, so that these derivatives won't have much room to change. And I was going to write something about the fact that the tendency of these derivatives to change is just equal to the second derivative of the function, the various second derivatives of the function, but we're not going to talk about that right now. Now I've used delta z for this distance, and I've used delta z for this distance, and I'm going to be a little sloppy with the notation here. I could put subscripts in these and do a lot of things that would be as confusing as what I'm about to do. So I'm just going to write part here and part here. And I'm not even going to subscript the part, so it still looks like the same symbol, but we understand that this delta z is the contribution that results from the rate of change of the function in the y direction, that is the y partial, and this is the part that comes from the partial derivative in the x direction, the rate of change in the x direction. If we look back here, this is going to be our value. From here to here is going to be our value of, or our approximate value at least, of z at the point x naught plus delta x, y naught plus delta y. And as we've seen before, this part of the diagram, let's go ahead and draw a couple of lines over here. This height is the same as this height. In other words, this height is f of x naught, y naught. Then from here to here, we have fy, delta y, fy being evaluated at x naught, y naught. And here we have fx, delta x, fx also evaluated at x naught, y naught. And we find that our total change in the function f is from this value, f of x naught, y naught, to the sum of these three values, which is f of x naught, y naught, plus the fy delta y, plus the fx delta x. And our delta f is therefore fx delta x plus fy delta y. Now, that's an approximation. Again, the values of fx don't stay the same as we move from here to here. The values of fy don't stay the same as we move from here back to here. Original function was f of xy equals to, let's make sure I've got this right, I'm going to confuse my y and x values if I'm not careful, 2y over x squared, so that fx equals derivative with respect to x is going to be negative 4y over x cubed. Fy is going to equal 2 over x squared. Notice that our fx is negative, meaning that if we go in the negative x direction, we will increase our value. Fy is positive, so we go in the positive y direction, we again increase our value, validating the general picture that we've drawn. Recall that our x naught was 3.6 seconds plus or minus 0.4 seconds. We're going to drop the seconds. We can worry about the dimensions and the units. They will work out, but we're not going to include those in our calculations. And y naught is 30 centimeters plus or minus 2 centimeters. That's 30 plus or minus 2. So that this is of the form okay, I just stopped in mid-sentence because I realize I have a notational error here. This should be x is 3.6 seconds plus or minus 0.4 and so forth. I'm going to not worry too much about that. I'm just going to say that this now says we have x naught y naught equals 3.6, 30 with the delta x of plus or minus 2 centimeters and a delta y of plus or minus 0.4 seconds. We're not going to worry about the units, so that's just going to be a plus or minus 2, and this is going to be a plus or minus 0.4. So that our delta f is going to be what? First of all, our fx. Now fx is 4y over x cubed, and it's going to be evaluated at x naught, y naught. Now let's just review. X naught, y naught is 3.630. Delta x is plus or minus 2. Delta y is plus or minus, and delta x is not plus or minus 2. Phooey. I've been mixing up my x's and y's, and this is all messed up. My delta x is plus or minus 0.4. My delta y is plus or minus 2. This problem originated when I wrote my x's and y's in reverse order here. I wrote them in that order for no good reason other than connotation of the letter x. So, delta x is our uncertainty in x. The 3.6 is plus or minus 0.4. The delta y is plus or minus 2. I've chosen to use a delta y of plus 2 and a delta x of minus 4. And now I should be able to evaluate these partial derivatives. Fx is just negative 4y over x cubed. Evaluating that at x naught, y naught, and being careful not to confuse my x's and y's, I have minus 4 times 30, y is 30, y naught is 30, divided by x naught cubed, which is 3.6 cubed, and that's times my delta x, which is negative 0.4. My fy is 2 over x squared, so that's merely 2 over 3.6 squared multiplied by my delta y, which is plus 2. Now we can calculate this, and I'm just going to write down a rough approximation. You can figure out the numbers. I think this comes around 0.6, and this comes out somewhere around 0.3, which is 0.9. Our conclusion, well, let's draw the conclusion in another clip.